This graph shows the historical pace of technological progress. For most of human history, it is a slow, creeping line. Then it hits a vertical wall, an intelligence explosion, where machines become capable of improving their own code at a speed we can no longer track. This is the theoretical concept known as the singularity. For decades, scientists treated this as a distant theoretical horizon. Inventor Ray Kurzweil based his models on the steady, exponential growth of computing power, famously projecting that we would reach this intelligence milestone in the year 2045. But over the last few years, the capability curve ran much steeper than early forecasters modeled. Groups that once placed artificial general intelligence 50 years out have drastically revised their timelines, with many experts now assigning a high probability to human-level AI arriving by 2029. Then the timeline collapsed completely. In July 2026, OpenAI CEO Sam Altman declared publicly that the transition was already happening, stating, "We are now in the singularity. This is the moment." We have to ask if this is a genuine intelligence explosion or aggressive corporate marketing designed to secure hundreds of billions in capital. To diagnose if human history has actually breached the event horizon, we need to clinically examine the technical symptoms of liftoff and the physical barriers trying to stop it. The primary diagnostic symptom of a singularity is recursive self-improvement. This is the feedback loop where an artificial intelligence becomes smart enough to write the code for an even more intelligent version of itself, triggering an accelerating cycle of upgrades. We are watching the leading edge of this loop form right now. Extrapolations of current coding benchmarks project a superhuman coder milestone around early 2027. At that point, AI systems will execute complex software engineering tasks faster and cheaper than the top human engineers at the frontier labs. This acceleration is driven by a structural shift in how these systems process information. For years, AI was limited by train time compute, which required developers to feed massive amounts of data into the model upfront. Now the frontier has shifted to test time compute, where processing power is allocated actively during the problem-solving phase itself. Instead of simply predicting the next word based on past training, models like OpenAI's O1 and DeepSeek's R1 use these test time processing cycles to actively think, verify their own logic, and reason through novel problems in real time. If we evaluate strict software capabilities, the system is exhibiting the exact mathematical symptoms of a runaway intelligence explosion. The code is actively getting faster at writing better code. Yet, if the software is caught in an infinite upward loop, human civilization has not fractured. Our daily lives look mostly the same. That is because digital algorithms are colliding with the physical world. Intelligence is a physical process. It requires electricity. As Elon Musk pointed out, the critical bottleneck for the industry is now the intelligence per joule ratio, a measure of how much actual calculation you get for every unit of electrical energy consumed. The first physical barrier acting as an immune system against runaway AI is the data wall. This chart illustrates the total global stock of high-quality, publicly available human text, roughly 300 trillion tokens of data. Researchers project that this finite supply is draining rapidly. Once that high-quality human data is exhausted, developers are forced to train new models entirely on synthetic AI-generated data. Doing so introduces the risk of model collapse, where the software steadily degrades by learning from and amplifying its own errors. The second barrier is the energy wall. Scaling AI is no longer a virtual exercise. It requires gigawatt-scale power, forcing companies to secure massive data centers, cooling infrastructure, and direct access to the electrical grid. Software algorithms might be mathematically capable of infinite acceleration, but they are trapped inside the uncompromising reality of copper wires, power permits, and semiconductor fabrication limits. There is a final constraint: slowing the singularity. The late Microsoft co-founder Paul Allen called it the complexity break. Allen argued that a superintelligent computer cannot accelerate irreducible physical timelines. A machine might invent a novel cure for a disease in seconds, but testing that cure still requires human clinical trials that take years to complete. Technological overhauls face the inherent friction of human habits, government regulations, and rigid physical laws. You cannot fast-forward the time it takes to pour concrete, build power plants, or change a society's behavior. Having an impossibly smart algorithm does not grant it the power to bypass the inherent slowness and complexity of the physical universe. The clinical diagnosis is clear. We are not crossing into a magical sci-fi singularity, where machines instantly reinvent the cosmos. We are entering what economists call an economic singularity. This is the point where artificial systems systematically take over nearly all economically valuable tasks, performing them faster and cheaper than human workers. This transition is not a blinding flash of light. It is a messy, bottlenecked, and massive physical infrastructure overhaul. The global arms race is a brutal competition to secure the raw materials of computation. Tech giants are hoarding massive plots of land, securing industrial cooling systems, and monopolizing local power grids. We are building a deeply integrated human-machine civilization. In this near future, software intelligence will be abundant and cheap, but physical power and real-world resources will be the ultimate currency.